Welcome. So let me show you how you can build a simple experiment with LLMs using our scenario builder. Now, in Alter Ego, a scenario is basically an experiment. It can contain all kinds of instructions, all kinds of rules, all kinds of algorithms that you would like. However, it turns out that many experiments follow the same structure. And that is the basic structure shown in this image here. So in principle, each thread, meaning each large language model, starts out with certain prompts to which they respond. Then their response is somehow filtered to only get what we want, for example, to only extract some sort of action. And then that filtered action is stored in the choices attribute of the thread. And that is repeated for every thread inside of a conversation. And that is repeated for each round, meaning over each round, the conversation, meaning the collection of threads inside of that experiment, stays the same. And for these experiments who follow this simple structure, you can use the scenario builder. Now, on this builder, we have a very simple example of a framed ultimatum game. And the treatments here were inspired by this paper down here. You can check it out. We do not use their instructions, but we only use their basic idea. So, first of all, we need to define who is actually participating in our experiment. Our threads, in other words. If you read our paper, you will find out that a thread is basically a source of text, and it can be a source of an action, obviously in an experiment. Now, we start out in this example with two very basic threads, two CLI threads. Now, if you run this experiment, as we will in a second, then you might be disappointed and you might think, well, what about LLMs? Well, some people do not presently have access to, GPT, and they still can check out how everything works by using these CLI threads. Furthermore, CLI threads are also useful for debugging and for testing your experiment. And that's what we're going to do now. You can also add threads, so you can have pretty much as many participants or as many threads as you like, and you can select from this variety. Others might be added in the future. And if you add a thread, you see it is added down there. But for this example, we will stay very close to what is built in. So let's remove this. Okay? So we basically start out with two threads, and they will be grouped together in a conversation. And to that conversation, a treatment will be assigned. And you can define your treatments down here. A treatment is basically just a string, a very simple word or a short phrase that describes the setting of the experiment. And I will show you in a minute how you can access the current treatment in your prompts. And you could add another treatment here. You could say another treatment. And then it would be added down here, but we don't need that, so we can delete this for now. So for now, we will start out with three simple treatments: give, take, and split. And what Alter Ego does in this build scenario here, it will automatically randomize and assign one randomly selected treatment to the conversation consisting of these threads. And by the way, let me just say that you can distinguish these threads by their index I, and you will see in a second where this sort of is relevant in your prompt. So you can assign roles to your threads. Okay, so we have treatments, we have threads. We can also, as shown above, we can also play our experiment for multiple rounds. So we have a very simple input field here where you can just say, you want to play it for 5 or 10 rounds. You can do whatever you want. Okay? So the minimum obviously is 1. And by the way, I should also mention this again. There is no rematching, okay? So the threads that you defined up here, they stay the same, they stay together, they share this common context, they cohere in this conversation, and they are not rematched or recreated, okay? So they basically stay the same, machine participants. Yeah, and then you can also have variables which vary between your treatments. So what is going on here is that I defined a variable called proposer instruction, and this takes on 3 different values depending on the treatment. So in the give treatment, the variable will equal today you can give money to the responder. In the take treatment, it will say today you can take money from the responder. And in the split treatment, this variable will take the value today you can split money with the responder. Okay? And as it turns out, if you add a variable, for example, we could add a variable called endowment, then again, you will get 3 fields, and you should set these values according to the treatment variation that you intend to do. Okay? By the way, the scenario builder will automatically recognize if you are using a string or an integer. And if you're using an integer or a float, like a numeric value, you can also do computations with these values. And I will show you an example in a second. But for now, we don't need the endowment variable, so we can just delete it. So let's just keep this variable up here. Now, we are almost halfway through. The prompts are the instructions of your experiment. And one thing that you might know from other software, especially O-Tree, is that you can access variables using this bracket notation. That's not all that you can do. You can also use more complicated statements using if, and you can also do loops using for. That is also supported. But most of the time, what you want to do is you want to access your variables that you define up here using these double brackets. A very important variable is the treatment.name variable. So using this variable, you can access whether you are in any of these treatments that you defined above. Furthermore, I already mentioned the I variable, which is a very short variable, but for each thread, I will be set to its index. So this was defined up here. You cannot change these indices, but you can access them. So you can sort of say, player 1 will be the proposer in our ultimatum game, and player 2 will be the responder. And that would be very sensible because that's how they run in, alter ego. So you can sort of distinguish threads according to their index. Furthermore, as I mentioned above, the response by the large language model will be filtered. And what remains in a filter is basically everything that you want. You separate the wheat from the chaff, so to say. And that what you want, meaning the action that the large language model took, will be stored in the choices attribute. And choices is basically also a variable, you could say, which you can access in your prompt. So for example, you can do choices, and then you have all the choices from all the previous rounds. You can also access the others choices. So if you have just one other player, meaning there are in total 2 players, you can do other.choices to get a list of all the previous choices. And of course, as you should know, in Python, if you have a list and you use the list index -1, you get the last element. So in other words, this expression up here will extract the just made choice, meaning the most recent choice of the other player. Of course, if you have more than 2 players, if you have at least 3 players, then other will not be set. Then you would have to use others. And others is, again, a list of other agents. The nice thing of using others or other is that you can directly access variables or parameters or attributes of these other agents. And that makes it very simple to access all kinds of variables or all kinds of things on the other players, on the other threads, in other words. Okay? So using this, we can already build a very simple experiment. And let me show you how this very simple experiment looks. Here we have the system prompt. And the system prompt basically sets the stage for the interaction, and it creates the whole setting, you could say. So what we have here might look complicated, but I'm happy to say that it's actually quite simple. The only thing you need to remember here is that parts which do not access a variable or which, do not use if or for, they will stay constant for everyone. So in other words, this here first sentence just stays constant for both of our threads. So both of our threads will be initialized using this very sentence. But then we introduced our roles. So here we check, are we currently dealing with the first thread? And if we are dealing with the first thread, then this particular thread gets the role of the proposer. And therefore we basically say, you are the proposer. This means that you will move first. Okay? So the proposer will see this sentence. However, the responder will see this sentence because the responder's I is 2, as you see above here. Okay, so the second mover, since this is a sequential game, a simple turn-based game, the second mover has the index 2, and only the index 1 gets this, and index 2 gets this. And this concludes the if block. So basically, this is the the dynamic part of this prompt. And then finally, we end up with certain typical instructions. We say, always follow the instructions, do not apologize, do not return anything except that which is expected. So this is a typical instance of prompt engineering. Okay? So basically, this shows you the essential features of alter ego, which is that you can have a prompt vary according to certain parameters, and that you can sort of dynamically vary parts or simple aspects of a prompt without you having to write like 2 different prompts. You can just write one single prompt, and you can have it vary in certain parts. Okay? And these are the parts that vary in this particular instance. So let us continue on with the user prompt. And the user prompt is the prompt that is repeated for every thread and every round. This here might also look complicated, but it too should be quite simple. First of all, even though this game just has one round, we start out by saying this is round and then a placeholder for the round variable. This is just a simple example which you could check out. And then if we are the proposer, we tell the proposer you are endowed with $10. Then the proposer gets their particular proposer instruction, which was defined up here. So depending on the treatment, they will be shown one of these 3 sentences. And then after they are shown this, this sentence that is varying by treatment, they will be told, after you make your offer, the responder will decide whether to accept or reject it. If they reject it, you and they both get $10 each. So in other words, this is just a very simple framed ultimatum game. And then we say, how much do you propose to keep? So of course, we need to get a certain response from the large language model. And in this particular case, we want the large language model to respond with JSON. Now, JSON is a language-independent text format for data exchange. And the nice thing about JSON is that it is supported by many large language models as a native response mechanism. And this makes it easy to filter, as we will see in a minute. So what we basically tell the large language model is that it should somehow decide how much money to keep from the $10, given the framing that we have. And then they should respond with JSON like this. So basically, they should return a JSON object where the keep attribute is equal to the actual amount that they want to keep. And this part here is a comment in JavaScript where JSON originates from. And the large language model would understand to put in the actual amount that they want to keep into this area here. Okay, so this is basically what will be shown in every round to the proposer. The responder, on the other hand, gets this here. And this too might look complicated, but it should also be quite straightforward. In general, we just tell the responder the proposer was endowed with $10. Here is their offer. Let's talk about this area here in a second. And then finally, the responder will be told, if you accept this offer, the offer is effectuated. If you reject the offer, you and they, meaning the proposer, get $0 each. Respond with either accept or reject. Okay? So this should all be quite straightforward. And then depending on the treatment, we, give another sentence about the offer that the proposer made. So what we say in the give treatment is we say the proposer decided to give you, and then we state the actual amount. And one nice feature of the templating engine used by Alter Ego, called Jinja 2, is that you can do computations on the fly. So we will obtain from this object here, by the proposer, we will obtain a JSON object with the attribute keep. And we can access this choice using this particular expression. We will say, what was the other's choice right now, meaning just before we came along, basically, before the responder came along. And then we say .keep. And .keep will access the amount that the proposer put into their JSON. Okay? And then, what is nice, as I said, we can do computations on the fly. So obviously, if the proposer decides to keep $9, the responder would get $1, meaning 10 minus $9. So we can simply express this calculation with this very expression here. So in the give treatment, the templating engine will create a prompt, which then will actually contain the actual amount that was given to the responder, or that was offered to the responder at least. Okay? In the take treatment, what we say is well, the proposer decided to take what they kept, So here we just straightforwardly access the other's choice that was made just now. And again, we do .keep to sort of access this particular amount, meaning the concrete amount that the large language model put in actually. Okay? And here we say, leaving you with, and here again, we have 10 minus what the other person kept. Okay, so this is basically just repeats what we showed up here. And in the split treatment, finally, we say, well, the proposer decided to split the amount so that they get what they kept, and you get 10 minus what they kept. So here again, it's quite straightforward. And this block here is varying. It is dynamic, and it will be changed on the fly by Alter Ego to reflect the actual circumstances of the situation. And then, as I said, the large language model will respond with either accept or reject. Now, the response by the large language model will need to be filtered in some way. The proposer responds with JSON, ideally, and the responder responds with accept or reject. And we can sort of create one filter for each thread in our experiment. So the CLI thread has to return JSON, as just mentioned. And we could change this filter to another one. And the second one, meaning the responder, thread index 2, he or she, they, you should say perhaps, should respond with accept or reject. Now, I think the JSON filter is quite straightforward because it basically parses what is returned by the large language model as JSON. So far, so good. However, the exclusive response filter is one of the filters provided by Alter Ego. And it basically looks for one of the tokens that you list in this very field. And you have to separate them by a semicolon. This check is case insensitive. So in other words, if the large language model responds with, given the offer, I will decide to accept, then this would be a valid response, and accept would be filtered. Okay? However, if the large language model somehow decided to respond with, I cannot decide whether to accept or reject, then this would fail. In that case, the current experiment would be stopped. Oh, sorry, actually the current, run would be stopped. The experiment would continue with another run, but the current sort of conversation would be stopped because then the response would not be unique. So basically, the large language model here is asked to respond in one of these two possibilities. And you could add more tokens that are allowed. But in principle, this serves the purpose of sort of, easing data collection with large language models, but also ensuring like a little bit of safety in how we actually interpret their response. There are also other filters, for example, the extract number filter, which extracts a single number. And as with exclusive response, if there are multiple numbers, then here too it will fail and the conversation will be aborted. Okay? There's also a non-filter, you could say, which is called as is, which basically accepts any response whatsoever. And you could also use this. This is useful for a dictator game, for example. In a dictator game, the responder must accept the offer. So in that case, you could use an as-is filter. Okay, so that's basically it. So now we've built a very basic experiment, which is shown in the example of the builder. And what we need to do now is we need to copy out this stuff here in this text area, which you, by the way, don't have to look at all. You just need to copy it out. And we need to put it into our projects folder in the file called build.json. So this really needs to have this particular name, okay? It needs to be called build.json. So let's actually do that. Let me select all, and let me copy. And then let's go to our editor. And here I can open Gini build.json. And here I've already prepared it, but let me actually paste it in fresh. So I just pasted in the value that we created from the builder. And as you see, the file is literally called build.json. You need to use this file name. Although for experts, there's a way to change the file name, but we won't cover this. This is stated in our README, okay? But you don't need to worry about that for now. So in other words, we have this build.json. And now, once we are in our virtual environment, we can run ego run build. And let me actually increase the terminal. Let's run this. And now you see two system instructions for two different CLI threads. As I said, the CLI thread is for testing your experiment. And since we have two threads, we get two system instructions. And you see the first CLI thread gets the proposer statement, and the second one gets the responder statement. Okay, so this has worked well. And then the first CLI thread, the 4BE91, will start. And the 4BE91 will start. You are endowed with $10. You can give money to the responder. So in other words, we are now in the give frame, right? And now we are asked to respond with JSON. So let's actually do this. Let's suppose that we keep 350. And then after we entered keep 350, the second thread, meaning the responder, is activated. And here you see that the computation worked out. We see, the actual value is put in, and it's computed by 10 minus $3.50. And now we can accept or reject this offer. So let's reject it. And that concludes the run of this experiment. By the way, you can run an experiment multiple times by doing ego run n, and then you could put in 42 build. Okay? And if you were to run this, then your whole experiment would run 42 times. Obviously, with the CLI thread, it's not too interesting, but once you use an actual GPT thread, this can be quite important so that you know how many times you want to actually run the experiment. Okay? But let's stop this for now. At the end, you will get this line that the experiment finished okay, and you can use this to export the data from your experiment. And what you can do here is you would say ego data build, and here you would put in the actual ID of the experiment. And this would show you this CSV output, which you can redirect to a file in a very simple way. You can just say, put it into data.csv, and then we can actually open the data.csv file. here just in the editor, but you could also open it in any kind of spreadsheet software. And here you get a CSV file, which basically contains the choice, the conversation that people were in, the experiment that ran, that is just the ID that I just showed you. You see the index of the agents. You see the round if you have multiple rounds. You see whether the thread was tainted or the conversation was tainted, and I will show you how this can happen in a second. Here you see the actual thread ID, you see the thread type, and you see the treatment that was assigned. So obviously, you could use such a file in all kinds of statistical programming languages to analyze it further. And you see here that the amount that was kept, meaning the response by the large language model, was put into the choice, as might be expected from the prompts. So we kept 3050, but still we rejected it as the responder. Now let me show you what happens when something does not work out well. So let's go back to ego run build. And now let's suppose that the proposer proposes in a valid way, 9. But now let's say, even though everything worked out fine, let's suppose that the responder responds with an invalid response. So what we could say is, I'm sorry, but I have no idea. In that case, the response would not conform to the exclusive response that we wanted and that we put in for the second thread, because neither accept nor reject are contained in this response. And you see that this leads to an exception, although the exception is caught. So if you have multiple runs, this will not disturb the other runs. It will only affect this particular conversation, which will actually terminate once an invalid response is received. Now let's take a look at what kind of data is exported in such a case. Let's go to ego data build. Let's output our data. And what you can see now is that the tainted column was set to true. And you see the choice here is sort of invalid, okay? But what you need to do once you analyze actual data from LLMs is you need to filter out those rows where tainted was equal to true. Because if tainted is equal to true, then that tells you that at least one agent responded in an invalid way. And in our previous example, we had tainted equal to false, which indicates that everything went as expected. So that is something that you need to keep in mind. If you use this for an actual project, you need to filter out those who have tainted equal to true. Yeah. So before we end today, let me actually show you how you can run a real experiment using a GPT thread. So for that, let's go to the top of our web app, of our builder, and let's delete the existing 2 CLI threads, and let's just add 2 GPT-4 threads. And now we replace the CLI threads with these GPT threads. Every other setting will remain the same, and especially the filters will also remain the same. They are not removed if you remove the thread, so they are remembered in a certain sense. But now we need to export this new scenario. And to do that, let's select all, copy, then let's go to our editor. Let's put it into the build.json. And now what we can do, we can simply say ego run build, and let's run it 5 times. And now every time GPT is invoked, you see this plus sign. So this is just an additional gimmick of, this builder functionality that the GPT thread sort of invokes this visual sign that it's working. Okay, so now we are already complete after just a couple of seconds. And as you see, we didn't input anything, so there was no CLI thread involved here at all. And what we can do now, we can go to the experiment, and we can say ego data build this, and let's output this to data CSV. We wrote 10 lines. And now let's actually open this in LibreOffice. So what you see in this LibreOffice is a collection of all the data that we collected. And as you see, it's 10 rows because we ran it 5 times. We had 5 runs of our experiment, and we had 1 round each, and we have 2 subjects, which in total gives us 10 rows of output. And here you see all the choices made by the AI. You see the index of the thread, as mentioned previously, and you see that it worked out very well in all instances because tainted is false for all the 5 rounds. Sorry, for all the 5 runs. And now you could take this data and you could sort of, analyze it in some other software. Yeah, that is how you can run a real experiment with a GPT thread. What you could also do is, of course, change one of the threads to be a CLI thread and another to be a GPT thread. So for example, you could go back to the builder and you could say, well, the first one should be human and the second one should be a GPT thread. So basically the human is now the proposer. We can copy this code to our editor into the build.json file. We can close LibreOffice for now. And now let's rerun this experiment. And let's see how it works. Let's just run it 2 times perhaps. So now we will take money from the responder. So I will take 9. Then GPT was just invoked, as you see, as the responder. Now again, we are in the proposer role as the CLI thread. And here, let's say I split 50-50. Now again, the experiment has concluded. Let's export the data. And let's open our data in LibreOffice. So here's the output. And as you see, when we kept $9, the AI rejected. And when we split it 50-50, the AI accepted in response. And here you see the different types of thread that we used. And you can, again, analyze this in whatever software you want. By the way, I'm just using LibreOffice here for expositional reasons. You can also use all kinds of other software that is able to read a CSV file. You could use Python, R, Excel, whatever you want. I personally like to use LibreOffice, but you can do whatever you like. So that is how you could use the builder to build your own experiment. You can have an arbitrary number of threads. You can have an arbitrary number of treatments. You can have an arbitrary number of rounds and variables. You can have your prompts vary according to treatments and according to roles of your players. And you can finally filter the large language model's responses by basically getting only what you want out of these responses. Let me say something else. So let's suppose that you're working on a project with a colleague and they send you, their build.json. Okay, so let's suppose that you receive this build.json here. What you can do is you can also copy it into the text area. So what you can do is you can sort of clear this out and you can paste it in, and this will update on the fly. So if your colleague made a change, you will see it reflected live in the user interface up here. And if you make a change at some position here, for example, let's add another response, then you also see that the build.json that you should use will also update automatically. So in essence, you can use this code down here to carry it over to the build.json file to run your experiment. But you can also receive others build.json. You can put it in there and you could import their code and have it reflected live here in this builder. So hopefully this makes it user-friendly to transfer code and transfer experiments between people and to change them on the fly and have the changes reflected down here as well. Thank you so much for your attention. Have fun and see you next time.